हरिः कर्ता।
So we have seen a lot of examples with the cross tabulation, and we understood the association between the various categorical variable. But the question arises: are they actually or really related, really connected, or really associated? To tell this, we need to dependent on one more tool. It's called chi-square test. Yes, the chi-square test is also a measure of association specifically used for examining the association between two categorical variables. I'm repeating it. The chi-square test is used to examine the association between two categorical variables, whereas cross tabulation is used to understand the association between the two categorical variables. So it assesses whether the observed frequencies in a contingency table differ significantly from the expected frequency. So assuming that there is no association between the variables, the hypothesis is there is no association between the variables. So now the next question that comes is how can we use chi-square with the cross tabulation? Because now we use chi-square test basically to tell whether the association between the two categorical variables is significant or not. I think you got my point. Now, now we'll use a chi-square test analysis with cross tabulation. So the chi-square static The chi-square static is the primary static used for testing the statistical significance of the cross tabulation table. Okay, so let me put the points whatever I'm making so that it would be much clearer for you. So let me write down chi-square test. The chi-square static is the primary static is used for the testing the statistical significance of the cross tabulation. Okay, this is the primary test or primary tool uh, to test the statistical significance of the cross tabulation. Then chi-square test determine whether or not the two variables are independent. Chi-square test determine whether those two variables are whether or not the two variables are independent. So if the variables are independent, that means no relationship. And then the result of the statistical test will be non-significant. Then the result, just note down the point, the result of the statistical test would be non-significant. There is no relation, so non-significant. And non-significant, and we are not able to reject the null hypothesis because I have told you before. So null hypothesis is nothing but it is no relationship or no relationship. So that means if the variables are independent, that means no relationship, and the result of statistical test would be no significant, and we are unable to reject the null hypothesis, which is no relationship. Clear? So now, uh, meaning that we believe there is no relationship between the variables. Simple. If you put it everything in a simplest way, there is no relationship between the variables. And so if the variables are related, then the result of the statistical test will be statistically significant. If a result is statistically significant, then there is a relationship between the variables. Then, and we can reject the null hypothesis. Here, we can reject the null hypothesis, and the previous one we are accepting with the null hypothesis. In the first case, if variables are independent, we are accepting the null hypothesis. If variables are dependent, or if there is a relationship, if they are statistically significant, then we are accepting the null hypothesis. Okay, that's what. And meaning that we can state that there is some relationship between the variables. The chi-square statistic, along with the associated probability of chance observation, may be computed for any table. If the variables are related, that's the observed table relationship would occur with very low probability, say only 5%. And we say that the results are statistically significant at the 0.05 or 5%. When do we say they're statistically significant? So if test statistic value comes around 0.05 or 5%, then we say it is statistically significant, or there is a relationship between the variables. Okay, so here we are rejecting null hypothesis. Next, and this means that variables have a low chance of being independent. That's what. So 0.05% is nothing but a probability. So this means that the variables have a low chance of being independent. So students of statistics will recall that the probability values 0.05 or 0.01 reflect the researchers' willingness to accept a type 1 error, or the probability of rejecting a true null hypothesis, meaning that we thought there was a relationship between the variables when there wasn't. We will look into these things in depth in inferential statistics. For now, just understand this condition. That's it. Furthermore, these probabilities are cumulative, meaning that if 20 tables are tested, the researchers can be almost assured that one of the tables is incorrectly found to have a relationship. So, depending on the cost of making mistakes, the researcher may apply more stringent criteria for declaring significance, such as 0.01, or sometimes you can go for the 0.05 also. So the researcher can declare the significance. This point has to be noted down. So let me put it. Researchers can declare significance. Could be 0.05 or sometimes 0.005. It's possible. So now let's compute the chi-square. Computation of the chi-square statistic for cross tabulation. So the chi-square statistic is computed by first computing a chi-square value for each individual cell of the table and then summing them up to form a total chi-square value for the table. So chi-square value for the cell is computed as observed value minus expected value whole square divided by expected value. Let me put this formula here. So chi-square value is equal to observed value minus expected value square divided by the expected value. That's it. This is your chi-square for individual cell, and summing up all the cells together, you will get the chi-square of whole table. Sum of all cells. So now let's look into the example that we have used for the cross tabulation also. So in this example table, so we observe that the chi-square value, uh, we observe that the chi-square value for the table is 19.35 here, that you can see here where my cursor is. The total chi-square of the table is 19.35 and has an associated probability of occurring by chance less than 1 time in 1000. So we therefore reject the null hypothesis of no difference and conclude that there must be a relationship between the variables. We can observe the relationship in two places in the table. So if you see that 0.00067, this is what the value that we have got. So with this says that for the degrees of freedom 4, and it says that there is a relationship between the variables or between the categorical variables. So hence you can reject the null hypothesis. Now the most obvious is in the chi-square value computed for each cell. So we observe that the cells Red Sox, Boston Red Sox, and uh, Blue Jays and Montreal and Red Sox and Montpelier, Vermont. So where were the three cells where the number of observed respondents was greater than expected. So we further note that when we examine expected and observed frequencies, the Yankees and Montreal, Red Sox and Montpelier, Vermont, and Red Sox and Montreal frequencies were fewer than expected. So because the cell chi-square and the expected values are often not displayed, this same relationship can be observed by comparing the column total percentage of the cell percentage of the row total. So in this current table, we observe that Red Sox and Boston. So Boston Red Sox had the greatest delta between the number of observed and the expected respondent. For any team preference, the city of residence. So however, we must be careful in concluding that the Red Sox caused respondents to move to Boston, or the Boston as a city of residence causes the fan loyalty. So Red Sox and Boston are the most observed fan and city relationship, but are most likely totally independent when considering the other concepts or relationships. So now cross tabs and chi-square are powerful ways to analyze your survey data, and another popular tool that makes an impact on research is called conjoint analysis that we won't be looking into, but still, so chi-square test is widely used statistical test for us. Okay, now let's take one example uh, for the chi-square test before we're wrapping up the chi-square test. We'll use pandas. Let's make our life simple. So we have the pandas. We have, okay, let me put everything. Let's import pandas as alias pd. Then I need to import chi-square contingency. Okay, directly I will import chi-square contingency method. Directly I'll import from stats module. I will import that. So from scipy dot stats, okay, from scipy package, bring from scipy package, find a stats module. From that stats module, import a chi-square contingency. You see that chi-square contingency. You got the chi-square gen, chi-square. I just want chi-square contingency. So let me import that. So what's the issue here? Cannot import chi-square content. Okay, sorry. Yep. So chi-square contingency has been imported. So now let's create a sample dataset first. So data is equal to a dictionary. Let's make a dictionary first. Okay, let me call this data. Yes, we got this data, but this is of different data. Okay, we'll do this example later. So for now, we'll do this one. Data 1 is equal to, let me make gender, sorry, male, female. Okay, let me copy this. Okay, so the first key value pair is ready. Now I just want to give smoker and smoker s and no, and repeat it. No and s, no. Yeah, that's it. Our dictionary is ready. This is our dictionary. Now let me convert this into data frame. So dfc, so df chi-square, dfc2, df chi-square, and pd, and then data frame of data 1. And here is your dfc. Yes, that's it. Your data frame is ready. Now it's time to create a contingency table. So contingency table or cross tab is same. So let's create a contingency table of gender and smoker. So contingency table is equals to pd dot cross tab, and inside that we'll take the dfc square, and first one is gender, and dfc square, second one is smoker. So there is some issue. Let me find out what's that. Smokeder. Okay, we got the smokeder. Let me change that. Yep, done. So our contingency table is also ready. So if you want to check the contingency table, let me call that contingency table. Here is your contingency table or cross tab you have seen earlier. So now let's perform chi-square test. To perform chi-square test, four parameters are important. So the first one is stat, the statistic, the value statistics, then p-value, then after the p-value we need to have a degrees of freedom, I'll say DOF, and after that we need to have expected value. So expected value, now for that I need to call up the chi-square contingency, and inside that I'm going to give the contingency table, and that's it. Now let's print each value. So first one is chi-square statistic, it's called chi-square statistic, and the value is stat. Print. And second one is p-value, the value is just p. And the third one is degrees of freedom, it's DOF. And the next one is expected frequencies, it's expected. And here are the values for us. You got the chi-square statistic, there is some amount I need to get now chi-square statistic. Okay, you got the chi-square statistic 0. I don't understand. Then the p-value is 1.0. It's closer to 1. Then degrees of freedom is 1. And expected frequency are 1.2, 0.8, and 1.2, 0.8. This in 1.8 and 1.2. So in this example, we first created a contingency table of gender and smoker using pandas cross tab method. Then we perform the chi-square test using chi-square contingency method from the scipy.stats module. The output includes chi-square statistic, p-value, degrees of freedom, and expected frequencies. The p-value can be used to assess the statistic significance of the association, where a p-value less than a chosen significance level. So we have chosen 0.05 as a significance value. If it is lesser than the 0.05, it indicates a significant association between the variables. If it is more than the 0.05, it's there is no significant association, and there we are accepting the null hypothesis in this case, where chi-square statistic is 0. So the p-value, where the p-value is greater than 1, so here we are rejecting the, so we are accepting the null hypothesis, saying that there is no association. So our null hypothesis is there is no association. Okay, if it is p-value is 1.0 here, so p-value, if it is less than 0.05, that's the chosen significance level, that indicates a significant association. But here we got, let me put it here, so p value is greater than 0.05, hence it says it's non-significant. So there is no relation, which also says accepting the null hypothesis. If you are not sure about what is null hypothesis and hypothesis, and I will be explaining hypothesis, null hypothesis, and true, false, and everything in detail in inferential statistic course, so don't worry. So next we will take one more example. So this time I'll take the data frame. See, this is what the data frame. I just want to do data, I want to do the analysis for this data frame. Okay, So let me take a similar one. So let me let me make a contingency table first. No, or else let's take up the actual data. So let's take anyone. So middle adults drop. Um, just let me give me one minute. So I just want to find out. No, the weight. Yeah, this would be better one because there is clear cut. Gender and weight categories. Let me put it here. Okay, this is our contingency table. Correct. So the relation we have seen, we felt there is some amount of no association, but between the gender and then weight. If men will have higher weights, whereas the women won't. That's what is my inference from this association. But whether that is significant or insignificant, I'm not sure. To make sure to confirm the significance of that contingency table or cross tab, I need to use chi-square statistic. Let me call the chi-square. Let me perform the chi-square statistic for that. So stat chi-square contingency. So here I'm gonna use cross tab WG WG here it is, and here are the values. So you got the chi-square statistic of 142, but the p-value is 1.37. So it's greater than, again it's greater than the 0.005. Okay, let me copy this. The same one repeats. Okay, it's greater than 0.05, and then again the degrees of freedom here is 3, and the expected values are expected frequencies are here. Clear? So let me take one more example, the recent one. Let's check this one. I don't think this also makes much sense. Age bins. Okay, age bins, and what's that? Age bins. Next, let me take one more example. Yeah, this one. Yeah, category bot, and then gender. Let's see how it works. Let me do the chi-square test there only. Yeah, yes, here. Yep. So let me do the chi-square test here only. This is quantity, and where is that the category? Yeah, here is the category. Yeah. So cross tab. So everything remains same, just category. And oh, this is better. It's not lesser than 0.05, but it's slightly better. There is some amount. And the chi-square statistic is 7.5, and then p-value is 0.37, which is not too far. Of course, when you compare with the previous values, it's slightly better. And then degrees of freedom is 7. But in this case also, we will be rejecting, we will be accepting the null hypothesis and saying that there is no relation at all. Okay, let's get into the height versus weight. I think that make some sense. Yeah, gender, uh, and then yeah, this one. Yeah, let me do here only. Let's perform chi-square test here itself. Just below that, gender and height. Let's see what it says. At least with this data, it's HG. Oh, this is too much. 9.6. It's 9.6, and degrees of freedom 2, and chi-square statistic 138. And if this one is also as greater than chosen significance value 0.05, hence we have to say there is no relation or association, hence we will accept the null hypothesis. So that's what the output we got with this, and this is what uh, a chi-square test for you. And I would like you to I would request you to explore more about chi-square test, and do a lot of chi-square test or statistical significance test for the measures of association using the cross tab or contingency table, so that it would be much clearer for you. So if you want to explore more, so you can get into my inferential statistic course, and you can watch about the chi-square test in detail.